Whenever the sun gets angry, it doesn't just produce light and energy, it also unleashes massive cosmic storms with the power to disrupt entire planets. So, what exactly are solar storms? How are they formed, and why can they have such a strong impact on Earth, affecting everything from power grids and satellites to GPS systems and even astronauts in space? In this video, we'll dive deep into the formation mechanisms of solar storms, explore dangerous eruptions like CMEs and X-rays, and examine their specific effects on our planet. This is not just a scientific story, it's a warning about a real threat from space, and a question of what humanity must do to prepare. What is a solar storm? A solar storm refers to powerful energetic phenomena occurring on the surface of the sun, including electromagnetic radiation, X-rays, solar wind, and especially coronal mass ejections, CMEs. When these massive eruptions take place, they release billions of tons of plasma containing charged particles into space at speeds of up to millions of kilometers per hour. If a CME is directed toward Earth, it can collide with our planet's magnetosphere, triggering a geomagnetic storm in near-Earth space. 1. Sunspots. Gateways to chaotic energy. Sunspots are darker regions on the sun's surface where the temperature is significantly lower than the surrounding areas, about 3,500 degrees Celsius compared to 5,500 degrees Celsius in the photosphere. But don't be fooled by their cool appearance. These are zones of extremely intense and complex magnetic activity, where powerful physical forces are in constant turmoil. When magnetic field lines become twisted to the breaking point, they can suddenly snap or realign, releasing massive amounts of energy in the form of solar flares and coronal mass ejections, CMEs. The number and intensity of sunspots tend to increase during the sun's 11-year cycle, known as the solar cycle. Monitoring sunspots is one of the primary tools scientists use to predict the potential occurrence of solar storms. 2. Solar flares. Rapid and intense bursts of light. Solar flares are massive explosions of electromagnetic energy occurring on the sun's surface, releasing large amounts of X-rays, ultraviolet radiation, and radio waves in a short time, ranging from just a few minutes to several hours. Although they don't eject large amounts of material like CMEs, the radiation from solar flares can reach Earth within minutes, immediately impacting the ionosphere and disrupting high-frequency, HF radio communications. Strong flares, such as X-class flares, can pose dangers to astronauts, damage satellites, or force polar route flights to alter their paths. Each flare is like a sudden lightning strike from the sun, and in many cases, they are accompanied by CMEs, doubling the threat to Earth. 3. Coronal mass ejections, CMEs. The tsunamis of space. If solar flares are attacks of light and radiation, then coronal mass ejections, CMEs, are heavyweight punches of mass and mechanical force. A CME can carry billions of tons of plasma containing charged protons and electrons, hurtling through space at speeds ranging from 250 to over 3,000 km/s. When a CME is directed at Earth and collides with the magnetosphere, typically after 1 to 3 days, it can trigger large-scale geomagnetic storms, distorting and shaking Earth's magnetic field. These events are responsible for stunning auroras, but they also pose serious threats, overloading power grids, knocking out satellites, and significantly disrupting GPS systems. Unlike the rapid arrival radiation of solar flares, CMEs offer a small window of time for humans to respond, but their impacts, if strong enough, can last for hours or even days. 4. The connection between phenomena, a chain reaction. Sunspots, solar flares, and CMEs rarely occur in isolation. They are often interconnected links in a tightly bound chain of solar activity. Sunspots are the surface manifestations of regions with intense and chaotic magnetic fields deep within the Sun. From these regions, magnetic energy can build up to the point of explosion, resulting in either a solar flare or a CME. A strong flare may be accompanied by a CME, or conversely, a CME might occur without any obvious flare. The relationship among these three phenomena is statistically and dynamically complex, making it a key subject of solar physics research. During the Sun's 11-year activity cycle, when sunspot numbers peak, the frequency of flares and CMEs also rises, significantly increasing the risk of intense solar storms. Understanding these interconnections is essential for developing accurate and timely space weather forecasting systems, helping to protect technology and human life from the threats posed by space. The mechanism of how solar storms affect Earth. Impact on the magnetosphere. The magnetic shield is distorted and shaken when a coronal mass ejection, CME, or a fast-moving stream of solar wind collides with the magnetosphere, Earth's protective magnetic field. It compresses and distorts its structure. The magnetosphere, often described as an invisible shield that blocks cosmic radiation and high-energy particles, gets pushed closer to Earth on the sun-facing side, while stretching into a long magnetotail on the night side of the planet. This interaction generates powerful electric currents in the ionosphere and radiation belts, causing magnetic fluctuations known as geomagnetic storms. These intense disturbances can last from several hours to several days, with widespread impacts on electronic systems and the near-Earth space environment. Impact on ground power grids. The risk of widespread blackouts. One of the most serious consequences of a solar storm is the emergence of geomagnetically induced currents, GICs, in large electrical systems such as power transmission grids. When Earth's magnetic field rapidly fluctuates during a geomagnetic storm, electric currents are induced underground and enter conductive systems, especially long high-voltage power lines that stretch for hundreds of kilometers. These currents can overload transformers, cause overheating, damage insulation, and in extreme cases, lead to widespread grid failures. A notable example is the 1989 blackout in Quebec, Canada, when a powerful geomagnetic storm left over 6 million people without power for 9 hours. In today's energy-dependent technological age, this represents a serious risk that meteorological and defense agencies monitor closely. Signal and satellite navigation disruptions. A shaken global system. Radiation from solar flares and CMEs not only affects the ionosphere but also penetrates deep into space, where thousands of satellites operate. GPS signals, which rely on radio waves traveling through the ionosphere to determine accurate positions, can be severely disrupted or distorted due to sudden fluctuations in ion density. In extreme cases, GPS accuracy can degrade from a few meters to several hundred meters, impacting civil aviation, maritime operations, military missions, and emergency services. Additionally, high-energy particles from the sun can penetrate satellite semiconductors, causing software malfunctions, hardware failures, and shortening the satellite's lifespan. Satellite operators often have to switch to protective modes or temporarily shut down operations to prevent serious damage. Threats to astronauts and space stations. While Earth is protected by its magnetosphere, astronauts in space, especially those aboard the International Space Station, ISS, or spacecraft, face significantly higher risks. When a solar radiation storm occurs, high-energy protons can penetrate spacecraft shielding and damage living cells, increasing the risk of radiation sickness or cancer. Agencies like NASA and ESA closely monitor solar activity to issue early warnings, allowing astronauts to take shelter in better shielded areas within the space station. Looking ahead, deep space missions, such as journeys to the Moon or Mars, will face even greater risks due to the lack of a protective magnetic field, making solar storms a constant threat that will require more advanced shielding technologies. Auroras, a magical beauty born from cosmic storms. One of the most visible and awe-inspiring manifestations of solar storms is the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. When high-energy particles from a CME collide with gas molecules in Earth's atmosphere, mainly oxygen and nitrogen, they excite these atoms, causing them to emit light at altitudes ranging from 80 to 300 kilometers. The result is brilliant ribbons of green, red, purple, or pink light that dance across the night sky. Although auroras are typically seen in high-latitude regions like Norway, Canada, Alaska, or New Zealand, powerful storms can push them much farther south, even as far as the southern United States or Central Europe. While their beauty may seem otherworldly, auroras are also a vivid indicator that Earth's magnetosphere is being violently disturbed by high-energy particles. When the sun gets angry, is humanity prepared to respond? Solar storms are not rare phenomena, but powerful ones capable of causing global-scale damage are often underestimated in public awareness. From causing widespread power outages, disrupting communications, interfering with GPS systems, to directly threatening astronauts and satellites, these impacts are not hypothetical. They have already occurred in history and could very well happen again, potentially with even more severe consequences in the near future. In a world increasingly dependent on technology and the digital space, having a clear understanding and thorough preparation for space events like solar storms is critical. Space agencies such as NASA and ESA, along with solar observatories, are constantly monitoring and studying the sun's activity cycles to issue early warnings. However, the responsibility doesn't lie solely with scientists. It also requires awareness from communities, policymakers, businesses, and individuals to develop proactive and effective response strategies. Because a sufficiently strong geomagnetic storm could alter the way we live, in just a few hours. And when that happens, will humanity be ready?